Hi, today I start fifth lecture and continue with the hybridization of carbon. As you remember, the carbon atomic number is the 6, and from here we can find the electron configuration of the carbon, and also the Valence-Shell electron configuration is this one, 2s2, 2p2, and we can draw it here. It is a ground state. In the ground state, we have 2 electrons in the valence shell in the S and 2 in the P. Okay? For this reason, depend on the hybridization, we can have a 3-type hybridization. And we can have a 3-type hybridized orbital, sp3, sp2, and sp. Okay. Now I continue all of the possibility to form of these 3 type of hybridization. As you remember from the last page, carbon is 6, and we have 1s2, 2s2, 2p2. Okay, it is in ground state. Okay, because the energy level in the last valence shell is very low between the s and the p orbital, we can have a promotion here or excitation, and 1 electron from the s orbital can jump to the p orbital. In this case, we will have a 2p1 and 2p3, 2s1, excuse me, 2s1 and 2p3. Okay, 1 electron in the S and 3 electrons in the P. Okay, the process, the promotion or excitation. And here, in this case, it is a excited state. Now, if we hybridization after all of these orbitals, 1s with 3p, we can produce 4 number of sp3 orbital with the same shape, and in the space or in the 3 dimension we can have tetrahedral shape for sp3, and the angle is 109.5. Okay, with this 4 sp3 we can produce 4 sigma bond. Okay, then all of the bond will be single bond. And as I mentioned, the shape is the tetrahedral and bond angle is 109.5. As you see here, s orbital is the spherical, and with 3 p orbital, which is in 3 axis, px, py, and pz. As you remember, the shape of the p orbital is a pair of the lobes on opposite side of the nucleus, because here is the nucleus, and the 2 lobes in the opposite sides, or we can say somewhere it's a dumbbell shape. Okay, as you remember, for example, methane is the C with 4 bond. Okay, if one of them is the S is spherical and the radius is shorter, and the p orbital is longer. In this shape, we will have this shape if we have with S and the px and the py and the pz, for example, if we have production of the methane. But in the practical, we see the size of the all bound in the methane is the same. For this reason, we have to hybridization these 4 bound, 1s with the 3p, and we can produce 4 number of the sp3, which the position in the space will be tetrahedral shape, and the angle is 109.5. But if we again start with carbon 6, And in the ground state, we have a 2s2 and 2p2. Again, we have a promotion or excitation here. Okay, and one electron jump from the 2s to 2p will have a 2s1 2p3. But now we use hybridization for 3 of them. Then pz will be alone there, and then we will have a 3 sp2 and 1 pz orbital. Okay, now we have 3, and if you see here, these 3 can make sigma bond or single bond. Then we can have the 4-3 sigma bond, 1 sigma, 2 sigma, this 3 sigma. Okay, but what about the pz? The last bond here, if you see, it will be pi bond. Okay, it is a pi bond with the pz. But the others here are sigma bond. How is it possible? It's very easy. Sigma bond with the angle of 120. It is trigonal planar. But the pi bond will be overlap each other and make a double bond or multiple bond or overlap, make a pi bond. If you see, I can show you for you. It is sp2, it is sp2, it is sp2 for the first carbon. For the second carbon again, this is sp2, this is sp2, it is sp2. One sp2 make a sigma bond. The other sp2 with hydrogen make other sigma bond. But we have here pz and from this carbon and pz from this carbon. If we have overlap of these two, okay, we can make pi bond. Okay, the rest of the bonds, the sigma is here. Sigma, 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 sigma. If we draw in the molecular shape, we can say green, carbon, hydrogen, 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 and the blue one is the pi bond. This is the pi bond, and the rest is the sigma. It is a sigma, it is a sigma, 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 sigma. And the angle is 120, and the shape is the trigonal planar. As you see here, if we have a s orbital, hybridization with a 2p orbital, we will have a 3 sp2 orbital, okay, which is a trigonal planar, and the angle between them is 120. And the last option again, when we have a carbon 6 and last Valence-Shell or Valence-Shell electron is the 2s2 2p2 in the ground state, and we have a promotion or hybridization, okay, one electron jump from s to p. In this case, we have this excited state, and in excited state, if we have a hybridization between 1s and 1p, we will have a 2 number of sp, and we will have a py and pz free. And I have to say the p orbital energy is higher than hybridization. Okay, and hybridized orbital energy is higher than s orbital. Now we will have a 2 sigma, 2 sp, and with this 2 sp we can make a 2 sigma bond, as I mentioned before. Okay, 1 sigma and 2 sigma. Okay, and with 2 other py and pz we can have overlap, double bond. Okay, this double bond is for these 2 and triple bond, but the simple single bond, it is for these 2 bonds. It's very important. With 2sp we can produce 2 sigma. Then we can produce 2 sigma with this one and 2 pi with these 2 p orbital. And the angle will be 180. And the shape is linear. For example, here 1s with 1 p orbital, and we will have a 2 sp orbital. The shape is a linear, and the angle is 180. Now we go to the molecular orbital theory. It mentioned electrons in a molecule are found in the molecular orbital. Is very important. Okay, molecular orbital is the combination of the atomic orbital. Okay, and these orbitals belongs to the whole of the molecule. It accepts building of principle, Pauli's explosion principle and Hund rule, which I explained in the first lecture. And it has a two position. It depends on the energy of the bonding. It can be bounding and anti-bounding orbital. In the bounding orbital is a low energy, it is more stable, and the anti-bounding orbital is high energy and less stable. For example, if you see hydrogen gas, H2 molecule exists, in this case we will have in the low energy this H2 orbital, okay, with one electron from this hydrogen and second from here, okay, they lose energy, and we can see it is a lower energy than atomic orbital, and we will have a bonding orbital. But if we have a higher energy in the hydrogen, we will see the free orbital. It is the anti-bonding orbital of the hydrogen with no electron. But for helium, which does not exist, helium-2, if we have a 2 helium, okay, if we would like to make it, in this case, we can have both bonding and anti-bonding. The first one is lower energy, the second one is the higher energy. And as you see here, we couldn't see this molecule in the nature. Okay, what's the difference between bounding and anti-bounding? In the bounding orbital, okay, electron distribution is almost between these two atoms, okay? But in the anti-bonding, between two nucleus, we couldn't find the electron. Usually we can find the electron in the other side, okay? And the distance is lower and usually has a very high repulsion, and this repulsion can cause high energy and low stability. Also, we can have the bounding and anti-bonding orbital or molecular orbital in the p orbitals. As you see here, if we have a overlap here, okay, same direction, it will be bounding. And if we have a different opposite direction, in this case, okay, between two nucleus, no electrons, and it can form anti-bounding orbital. Now we go to the molecular geometry or VSEPR model or Valence-Shell Electron-Pair Repulsion model. Okay, it is a spatial arrangement of atoms in the molecule. Okay, it helps for the prediction of the molecule shape and the form and the angle and the structure in the space. Okay, Valence-Shell electron-pair arranged with atoms, and also it depends on the electron pairs which are far away from each other as possible. Then the minimizing of the electron pair repulsion, because as I mentioned, if we have a high repulsion, we have a low stability okay, and in this case molecule has a low stability, then the structure will be unstable. Okay, from the molecular geometry, for example, if we have a AX2, usually A is from the second group, alkali metals, and if we have and the bond with the other, for example, other element or molecule, or for example with the halogens. In this case, the angle will be 180 and the shape is the linear. But if we have a 3 bonding AX3, okay, central atom without pair electron, lone pair electron, in this case angle will be 120. Usually the A can be group 3, boron group, for example BF3. Or if we have AX2 with one lone pair electron like this, okay, this is usually, it is almost unstable situation, and usually we can find in the group 4 also, germanium difluoride, the angle, it is a band and the angle depends for the repulsion of this double bond. But if we have a 4 bond with the central atom, usually it is group 4, the shape is the tetrahedral and the angle is 109.5. In the carbonate, the shape is sp3. But if we have 3 bonding and 1 non-bonding, electron pair, for example, AX3 with 1 non-bonding, it's group 5 is the most important example is the ammonia. Okay, it is the pyramidal because of the effect of these pair electron in the shape. And if we have a 2 bonding and 2 non-bonding, it is a band like water, because in the water we have a 2 pair, lone pair of electron. For example, here, it makes this shape is the band also, but the angle is lower. Now we go to dipole momentum. Dipole moment, it shows the quantitative measurement of charge separation of the between 2 atoms in the molecule, okay, or in the whole of the molecule. For example, if you see here, it is a Cl2, okay. It is almost symmetry because both of them are chlorine and the electronegativity is the same, and then it will be symmetric. It is then dipole moment is the 0. Dipole moment is when it's the 0, it is non-polar. But it is a very good rule we studied before. If the electronegativity less than half, okay, in this case, it is a non-polar, okay, it is a non-polar. But as you see in the HCl, hydrogen chloride, chlorine has a high electronegativity compared to the hydrogen, okay, more electron goes to the chlorine side. And in this case, the shape will be like this, and the chlorine side has a more probability of has an electron, and in this case, we will have a partial negative for of electron in the chlorine side, and partial positive for hydrogen. The shape is the asymmetric, non-symmetric, and the molecule is the polar. Also, we can say non-zero dipole moment. Dipole moment is non-zero. It is a polar covalent bond. As I mentioned before, for polar covalent bond, the electronegativity difference must be bigger than 0, is smaller than 2.1, because more than 2.1, it is the ionic bond. It cannot be covalent bond. Then, in the end, we can say, if the dipole moment is 0, it is a non-polar, the electronegative difference is less than half. And if dipole moment is non-zero, the molecule is the polar, and the electronegativity difference is between half and 2.1. Okay, for example, there is some exception also, but not exception because also the other important things. When it is a dipole moment is 0, molecule is symmetric as I mentioned. Here, if you see here, we have electron pair here, but this molecule, carbon dioxide, is a symmetric, you see, okay? Central atom hasn't any electron pair, and dipole momentum is 0. It is a non-polar, and also, as I mentioned, it is a symmetric. But in the hydrogen, in the water, but okay, we have 2 hydrogen again the same. But because of this electron pair of oxygen, the shape is asymmetric, non-symmetric, or asymmetric. And the molecule is the polar. Okay, because it has a dipole, because if you see hydrogen side is the positive and the oxygen side is the negative. And here the dipole momentum here is the non-zero, and here is dipole momentum 0. Polar covalent bond and associated geometry. We go to the next part, is the ionic bond. As I mentioned, if the electronegative difference between two atoms are more than 2.1, in this case, the bond is ionic bond. Okay, ionic bond, the electrostatic attraction between the positive and negative ion. Then we can say ionic bond is between cation and anion. Okay. Is you see how we can make this one. For example, here we see the cation is the, usually cation is, we can classify as the monatomic, like from metal, like sodium plus, or polyatomic, like NH4 plus, ammonium. Anion also can be monoatomic, like Cl minus, and polyatomic, like carbonate ion. How we can make it? For example, we have a sodium from first group, alkali metal, and the chlorine from the halogens. Okay, we know from the last lectures, sodium is a metal, has a ionization energy, then he would like to lose of the electron. Ionization energy is this number. Chlorine has a high electron affinity, would like to accept the electron, become an ion, and it is electron affinity is this number. But the most important for the ionic bond formation, we need a lattice energy to make a network of the cation and anion. It is a negative. And the total energy between formation of the cation and anion will be negative. Because of negative, it is exothermic, and the energetically is more favorable. And also usually accept the octa rule because of this chlorine accept the electron and become noble gas after itself, and the sodium loss of electron become cation is the noble gas before it. Okay. As you see here, lattice energy also, every cation has a neighbor of an ion. Okay, it is a lattice system or network. As you see here, we can have a central or faced crystal and many shape and salts with a high melting point. These has ionic bond. Then we can say ionic solids. Usually they are salt. I think is one of the important definition. Again, what I mentioned, classification of ions. Ions can be anion and cation. Okay, again, anion or cation, both of them can be polyatomic and monoatomic. Usually, monoatomics in the cations, it is from group 1, alkali metals, and group 2, alkali earths. Okay, we can say, I can write from the first group, Na plus sodium ion, potassium ion, lithium ion, and from the group 2, it is a beryllium, magnesium 2+ ion, calcium, and other strontium also can be, and barium also can be. Okay, from the group 3, aluminum can be also Al3+. Usually we can have from transition metals. For example, but transition metal has a different oxidation number, then we can have, for example, Fe2+, Fe3+, or Cu2+, Cu1+, Mercury 2+, Mercury 1+. They are usually, all of them is monoatomic. For example, also silver 1, Zn2, and Mercury 2, it is a monoatomic. for the naming for the metal is very easy. We use the name of the element plus ion. It is a sodium, and we say sodium ion, zinc ion, okay? But in the transition metal, if we have two possibility, we use Roman numbers. For example, Fe2 plus, Fe3 plus, we write iron, 2 ion, iron, 3 ion. Okay, but for anion, we use the esteem name of the element. For chlorine, we use chlor and add ide. Bromine, bromide. It is a two parts. Okay, the first part is the esteem name of element, and ide is the suffix of ide. Bromide, chloride, iodide, and it's a polyatomic. Okay, for the cation we don't have a lot of example. For example, we have ammonium and we have a mercury one, but for the anion we have a more carbonate, sulfate, sulfite, phosphate, nitrate, and nitrite. Okay, if we have just one example for one central atom with oxygen, usually the second element is oxygen. In this case, we can have a 8 suffix, carbonate, okay? But if we have a two possibility, okay, higher oxidation number has the suffix 8, lower oxidation number has the suffix 8, nitrate, nitrate, and nitrite. Okay, for example, phosphate and again sulfate with a suffix because the big, and we have a sulfite. Again, but for the other one, we have a two. For example, chlorine, polyatomic, we have a 4 example. 2 higher oxidation number is 8. 2 lower oxidation number is 8. But the highest one accept prefix per, and the lowest one accept prefix hypo. Then hypochlorate, perchlorate, chlorate, perchlorate, chlorate, because both of them is 8, and the second two lows is the chloride and hypochlorite. But it's very easy. If we have 8, when we make acid, 8 convert to the ic acid. For example, carbonate, carbonic acid, nitrate, nitric acid, phosphate, phosphoric acid, sulfate, sulfuric acid, perchlorate, perchloric acid, chlorate, chloric acid. But it change to ous acid. Again, it change ous acid. For example, nitrite, nitrous acid, sulfite, sulfurous acid, chlorite, chlorous acid, hypochlorite, hypochlorous acid. As I mentioned, the rule, what I explained is the same. We can have the suffix 8 and it, 8 for the higher oxidation number, 8 for lower oxidation number. Okay. Also, we can say the 8 for the great number of oxygen atom, or 8 for the less oxygen, again oxidation number. And if we change to the, and if we have a more possibility, pair the highest oxidation number, okay, and the hypo is for lowest oxidation number. And when we want to make acid, 8 convert to the ic acid. When we change to the E to the acid, will be ous acid. Okay, the rule, 8 convert to the ic acid, 8 convert to the ous acid, carbonate, carbonic acid, nitrate or nitrate, nitric acid, nitrite, nitrous acid, phosphate, phosphoric acid, sulfate, sulfuric acid, sulfite, sulfurous acid, because we have a 4 possibility: perchlorate, perchloric acid, chlorate, chloric acid, chlorite, chlorous acid, the lowest number of oxidation number, hypochlorous acid from the hypochlorite is the hypochlorous acid. Rule of the writing formula for the salt is very easy. First, we use the cation name without the cation, and then we can write anion name, okay? And usually we convert the oxidation, the charge between the cation and anion, and the net charge must be 0 in the salt. For example, we have a positive charge here, negative charge here, both of them 1, we can produce 1 sodium bromide. But the calcium, we have a 2 here, we give for the bromine. Bromine is the 1, we give here the 1, okay? And because I have here 2 brom, I have bromide, we put 2 behind the bromine. And Na2S2S I give for the sodium. Then sodium come here. Now we have 2 sodium. I write 2 sodium in the back. Both of them is the 1, and we don't need to do anything. Again, both of them is the ammonium chloride or chloride and ammonium nitrate, the same. But for the ammonium sulfate, when we want to give a 2 for the here, we have to make a circular bracket, and I have to put bracket here and put 2 here, and I have 2 ammonium, I put here 2, and calcium nitrate, again we put this 2 again for the here, and we have a 2 nitrate, and we can put here, and the calcium carbonate, both of them has the same same charge, and they can cancel each other. But here we give a 3 for here, and we give a 2 for here, then 2 will be here, 3 will be here. Now we have 3 calcium behind it, and 2 phosphate behind it. Okay, also aluminum, we give a 3 for here, we have a give 2 for here. Okay, we have a 3 carbonate here, and then we put 3 here, and we put here 2 here. It is a rule again. I can say the names: sodium bromide, calcium bromide, sodium sulfide, ammonium chloride, ammonium nitrite, and ammonium sulfide, calcium nitrate or nitrate, calcium carbonate, calcium phosphate, and aluminum carbonate. Okay. I stop here the lecture. I hope it will be useful, and see you in the next lecture, and continue with this lecture. Have a good time, and I wish the best for you.